Um, so welcome to the weekly colloquium of the School of Astrophysics. We are glad to have Professor Kanan Kumar Datta from Jadavpur University as our speaker today. So Professor Datta did his BSc and MSc from Bardhaman University and then went to IIT Kharagpur for his PhD, where he worked with Professor Somnath Bharadwaj on reionization of the universe. There is a very big reionization community in India, like many other communities, but the unique aspect of the reionization community is everyone did their PhD with Professor Somnath Bharadwaj. So he is one of the first ones. So after his PhD, Professor Datta went to Sweden, Stockholm University, where he was for 4 years. Then he came back and became a postdoc at the National Center for Radio Astrophysics for a year, and then joined Presidency University Physics Department as a UBC faculty teacher fellow. So he was our colleague for almost 8 years until 2022, when he moved to Jadavpur University. It was our loss because Professor Datta, particularly the students' loss, because Professor Datta has been very involved with students during his stay at Presidency. Many students did their BSc and MSc projects with Professor Datta. They wrote their first papers with Kanon. Many of them are doing PhD at various institutes in India and abroad. I think at least one of them is here. Orijit did his BSc project with Kanon. Orijit actually, who just defended his JRF to SRF assessment yesterday and taking a break today, actually did his master's project with Kanon and was very close to writing a paper when he moved on to other things. But he still sort of hopes that someday he'll get back and do the same thing. One of the first PhD students who got their degree from as a School of Astrophysics member, Dr. Ankita Bera. She did her PhD guided by Professor Datta along with Professor Shami. So not only that, Kanon used to always challenge students for cricket games, and he is a very good pace bowler. So if you can convince him to go to our picnic in the coming picnic, then you will see that pace bowling. Yes. And also there is Professor Devashish Majumdar, with whom Kanon has collaborated on a very important sort of dark matter, a signature of dark matter project. So, and also since Kanon is in many committees in our department and in our university, so in a way we don't feel like he is in a different institution, but he is. So with that, and as I discussed, his expertise is in the sort of the reionization universe and the various sort of theoretical aspects and observational signatures, prediction of observational signatures from the reionization era. So, so let's hear from Professor.
Okay, thank you, Ritavan, for your very kind introduction. And thank you, School of Astrophysics, my colleagues Somodip and Sujatana, for hosting me here today. As Ritavan sir already told you, I was here from 2014 to 2022. And so I joined here as a teacher. I don't know how much I could teach you, but I can surely tell you that I learned a lot in this place, more than I could teach. I learned from students, I learned from our colleagues. So, and some of the things that I will show you today actually has been done here, and I'm still carrying that things at Jadavpur University. Regarding this colloquium, it's a very unique thing at this School of Astrophysics. Earlier, it used to be at physics department, and I must thank and congratulate Ritavan, Suchetan, and Somodip for organizing this for such a long time on an extremely regular basis. And this is, I think, is a very excellent opportunity for students, particularly that you get to learn, hear from many eminent scientists from all over the globe, and you don't see it in many places. So this is very unique and a very good opportunity. And to organize that continuously for a longer time, uh, I mean, you need dedication, enthusiasm, and hard work. So yeah, so congratulations, all the astrophysics faculty members. Yeah, so today, okay, আমার গলা একটু মানে আজকে প্রবলেমেটিক, জানি না হাউ লং আই কুড সার্ভাইভ। আপনারা বুঝতেই পারছো, শুনতে পাচ্ছি পিছন দিকে সবাই, তাই তো? Okay. Okay. Uh, so today I plan to talk about thing that I have been working for the last 2 decades. That is epoch of reionization and cosmic dawn. And so this is a kind of overview talk. I will just overview the field. There are a lot of exciting things happening at this moment. So I'll give you a flavor of those. I'll not go into the very technical details. I'll keep it at the very at a level that I think students can understand. So professors may feel bored here. So sorry for that. Okay. So I also allow you to interrupt me during the talk. I mean, if you have any questions, doubts, you can raise your hand and ask me questions. So this is the title of my talk, lighting up the first billion years. So I'll talk about the first billion years of the universe. You know, the current age is only is 14 billion years. I'll talk about only the first billion years. So this kind of talk always starts with this kind of picture, and you have seen it many times. But without this picture, the talk is not complete. So I'll just go through it. So this is a diagram that shows how our universe evolved from the Big Bang to the present universe. And so this is the time when the universe started with the Big Bang, and this is the time increases along this line. So this is our present universe. When universe was 400,000 years old, this famous epoch of recombination happened. And during that time, the radiation background decoupled from the matter, and that radiation background free streamed, and we still see that radiation today, and we know it as a cosmic micro background radiation, which we have heard and also learned from your classes. So after that this famous recombination epoch, universe entered into the epoch called dark age. And this is the epoch of dark age, and dark because there was no luminous sources during that time. Like fast star, like galaxies, stars, black holes, nothing were there. And yeah, so that lasted up to 0.2 billion years, that is 100 to 200 million years. And it is believed that around that time, fast luminous sources, the stars and galaxies started to form, and universe suddenly became visible, because when you have stars, it makes the surroundings visible. So that's why this is called a cosmic dawn. It's like dawn of the day. So, and then initially the radiation from those sources started to heat up the intergalactic medium initially, and then later UV radiations from those sources started to ionize the neutral hydrogen. So neutral hydrogen, so universe became neutral after the recombination epoch. So universe became fully neutral during the dark ages, and out of total, so you have 4% of baryon. Out of that, 75% was in the form of neutral hydrogen, and 24% was in the form of helium. And that so now reionization process started around that time. So radiation from the first sources started ionizing the neutral hydrogen background, and that process continued for some time. And then reionization probably ended when universe was 1 billion year old. So I'll talk about so in today's talk, I'll talk about up to this period. So basically, I'll focus on these two important epochs, that is cosmic dawn and epoch of reionization. And after that, reionization universe was almost ionized, but still 1% neutral hydrogen left mostly in galactic environment. And that is also important because now we can also detect that 1% neutral hydrogen through 21 centimeter radiation and study a large scale structure of universe. Okay, so that was the broad picture. And now, what are the main science questions that we want to know answer of those? First question is, when exactly the first sources appear in our universe, and when exactly the reionization took place. So whether it is early, like whether it happened at rates greater than 10, or whether it is late, and whether it is extended or rapid. These are the questions that we do not know the answer of. Then how did the reionization process? Like you have these ionizing sources, and it will create ionized regions around them, and that ionized regions grow with time and overlap with the surroundings. So that is the current picture we believe in, but there is no observational evidence of that. So we want to know the answer of that. And what are the sources that are responsible for ionizations, like whether it is stars that created ionization, or AGN, or even if it's a star, whether stars in dwarf galaxies or massive galaxies, we have to know the answer of those things, right? So these are the key questions of this topic. Now, what we know about the epoch of reionization? So there are several observational probes that give you some information about this epoch. And the first observational probe actually come from observations of cosmic micro background radiation. So observations of cosmic micro background radiation tell us that the midpoint of reionization is around 7.7. And so that suggests that universe may be, reionization may be very late and rapid. And it also suggests that universe was less than 10% ionized above redshift 10. But then another set of observations come from quasars absorption spectrum. So if you observe quasars absorption spectra, and that tells us that reionization probably ended by redshift 5.3 to 6, slightly lower than what we believed like 5-6 years back. So people are arguing that reionization did not end at 6, but it ended at 5.3 or something like that. So yeah, but this set of observations tell us that reionization probably is late and rapid. However, recent observations by JWST, so it observes very high redshift galaxies, and that probably hinting at early reionization. So these observations are consistent with early reionization. So there is a debate whether it is late or whether it is early, whether it is rapid or whether it is extended. So these are the debate currently going on, and people are trying to find answer.
To say that midpoint, that 7.7, that is from CMB polarizing. That initial information is from CMB polarization.
Yes, yes. So that's the optical depth basically.
How you model that?
Yes, so this is basically if you assume sudden reionization. So reionization happened overnight.
No, but the optical depth is obtained from what? From optical depth is obtained from
polarization.
From polarization to there it is lot of model.
Right. So now we understand that there are a lot of questions, and also the existing experiments give you some information, but there are also debates. So then we want to know the details of the reionization process, and also we want to settle the debate that is currently going on. And so one of the most promising tools to study the epoch of reionization is, of course, observations of redshifted 21 centimeter signal originated from neutral hydrogen. Okay, so now I mean, these slides are for students. So refreshing your knowledge about atomic spectra. So this is the hydrogen atom, and this shows the energy levels and the different transitions. Today, I will focus on the ground state of neutral hydrogens. You have many excited words, but I will ignore them. I will focus on the ground state of neutral hydrogen, and that's because the neutral hydrogen that is abundant in our universe, particularly during the epoch of reionization and cosmic dawn, most of them were in the form of atomic hydrogen, and they were in ground state, right? Then if you focus on the ground state, there is a phenomena called hyperfine splitting. So hyperfine splitting is basically so in the ground state, for the ground state neutral hydrogen, so you have electron and proton in a neutral hydrogen atom, and both have magnetic dipole moments because of their spin. They have dipole moments, and magnetic moments of proton that produces magnetic moment of proton at the center, that produces magnetic field outside, and electron on the outside, it experiences that magnetic field. So that is the interaction. So you have the magnetic field created by proton spin, and that is experienced by electron. So there is an interaction between proton magnetic moment and electron magnetic moment, and the corresponding potential energy is mu dot B, where mu is the magnetic moment, B is the magnetic field. So this is, I think you have already learned it from your quantum mechanics class or maybe atomic physics class. Then if you calculate it, you will get the correction to the ground state would be this, because of this interaction. So you have this ground state energy 13.6 electron volt minus 13.6 electron volt, but on top of that you have this correction because of this hyperfine splitting. And you see these are the constants, but you have S dot I, which is S is spin of electron and I is the spin for proton, and both are half spin half particles. But when you have interaction, so you can write this S dot I like this, where F is the total angular momentum, and ground state has zero orbital angular momentum. So it's basically total spin angular momentum. And S dot I is it has this value minus 3/4 h squared square when F is 0. F is 0 means the total angular momentum 0 when the electron spin and proton spin are anti-aligned. And when they are aligned, proton spin and electron spin are aligned, they have F value is 1. You can calculate this S dot I to be as this. Now, the energy difference between triplet and singlet state is this, which corresponds to this value 1422, of course. But if you include more precise QED calculation, it will give you 1420 megahertz. So that is the basic physics behind the origin of 1420 megahertz line. And if you convert it into wavelength, it will give you 21 centimeter, right? So so this is the calculation, and it was first theoretically predicted in 1944 by Henrik van der Hulst. So this person actually predicted the existence of such line, and it was experimentally observed in 1951 by A1 and Purcell. So this is the telescope. It is a radio horn, like a horn antenna radio telescope, and it was set up at the terrace of that institute. It's not that big compared to the current radio telescope, but using that telescope, they detected first 21 centimeter signal coming from our own galaxy. Okay, not from epoch of reionization. That is very difficult, and we haven't done that.
It's the same 8% who put the Berkeley.
Yes. Electromagnetism.
Okay. Right. Yes. So now, why we are so concerned about hydrogen? Because you know that out of 100% of total energy budget, only 4% is baryon. But out of this 4%, 75% is in the form of hydrogen, and 24% helium. So universe is basically filled with hydrogen. It is there everywhere. Now, when you observe at line transitions, so when you observe at line transitions, actually, you can set up your observing frequency so that you can actually probe our universe from redshift Z to 200 using this line. So this is a very unique probe because it will allow you to observe our universe from redshift 0 to redshift 200. And I don't think there is any other probe that can do the same. And it can observe the large scale structure of our universe. So you can see the evolution of universe in principle by observing this line. And and this signal can also another advantage is that signal can be observed from the Earth's surface. So you can build a radio telescope at the ground, and you don't need to send it to the upper atmosphere or space. So these are the advantage. And so we are so concerned about this line. Now, what kind of signal we are going to measure? So the quantity of interest or quantity that we can measure is called the differential brightness temperature. Differential brightness temperature of 21 centimeter signal. And this is defined as this. So Ts is the spin temperature, T gamma is the background CMB temperature, tau is the H1 21 centimeter optical depth, and the whole thing is redshifted. That's why you have this 1 plus Z factor. Now, what is spin temperature? So spin temperature can be defined as this. So we have, as I said, the hydrogen ground state can have triplet state and singlet state, and you can actually write that ratio in terms of spin temperature. So basically, it quantifies the amount of neutral hydrogen that will be there in triplet state and singlet state. And of course, so basically, if you just want to picturize this equation, so I have shown you a figure. You have this background CMBR coming from redshift 1100, and that radiation passing through neutral hydrogen during the epoch of ionization and cosmic dawn, and it is observed by telescope at the ground. Now, so this neutral hydrogen cloud can be parameterized by two quantities, that is gas temperature and spin temperature. And so spin temperature can be written as this. Now, if spin temperature is different from the background CMBR temperature, you will have non-zero signal. So you can only see this radiation when spin temperature is different from the CMBR temperature. Otherwise, you will not see anything. For example, if you have ionized regions, there will be no neutral hydrogen, then this signal will be zero. So inside ionized bubble, you have 0 21 centimeter signal. Outside it, you will have some non-zero. It can be positive or negative depending on whether T spin is greater than TCMB or less than TCMB. If it is greater than TCMB, you will have positive signal. If it is less than TCMB, you will have negative signal. So both are possible. Okay. Now, if I write this delta TB, derive this equation, we will have this kind of equation. So differential brightness temperature is it can be calculated using this formula. Now you see there are many quantities. XH1, that is a neutral fraction. So how much hydrogen is neutral? If it is fully neutral, then XH1 is 1. If it is fully ionized, XH1 is 0. That means when you will have 0 signal. Then you have this spin temperature, and so these are the quantities that is directly related to your astrophysical sources. So astrophysical sources like galaxies and stars, they will ionize the medium, and depending on how the models that you consider, you will have different XH1 distribution and TS distribution. And you see this is a quantity which is dependent on redshift, as well as it has spatial dependence. Like XH1 may not be same everywhere. It will be 0 very close to the source. It will be 1 very far from the source. Spin temperature is also very high, very close to the source, but it is much lower when you go far away from the source. So you have spatial distribution. But then delta TB is also dependent on H, that is Hubble parameter. And Hubble parameter means it includes all these cosmological parameters. It also depends on density distribution. Delta B is the density over density parameter. Now this delta, so that means this delta TB contains an enormous amount of information about the astrophysical sources, about your cosmology, and also your background matter distribution. So that's why it is so, I mean, very powerful, and it contains huge amount of information. However, the signal is extremely weak, and that's why no one could detect the signal as of now from the cosmic dawn on an epoch of reionization. It's extremely challenging task. I would say this is one of the most difficult job in modern cosmology to detect such a signal from cosmic dawn. So that's why people are trying and people are building new telescopes. And so I'll show you some of the developments. Why this is challenging? Because signal is weak but detectable. But the problem is that at the same frequency, our own galaxy and other galaxies, the foreground galaxies, emit strongly. So, for example, at the back you have 21 centimeter signal, and it is of the order of few millikelvin. The strength of the signal is few millikelvin. But if you look at the emission from our galaxy, it is about Kelvin order. So already 1,000 times stronger than the expected signal. So when you observe using a telescope, you observe everything, right? So you have few millikelvin signal plus some 1,000 millikelvin. I mean 1 Kelvin, right? So that is a big challenge. You have to subtract them out, and so not only signal from our galaxy but from other galaxies, extragalactic radiation, supernovae, and so these are the main challenges. However, there is one good point about this 21 centimeter signal is that the 21 centimeter signal, if you plot as a function of frequency, it fluctuates. It's kind of random, not fully random, but it is kind of random. So it changes a lot if you plot as a function of frequency. However, foregrounds, which are smooth, mostly synchrotron radiation coming from our own galaxy, and that are expected to follow power law. So it is very smooth. So that allows you to disentangle these two components in principle. Okay, of course, it is very difficult job, but in principle that allows you to separate them out. Okay, now what we are going to measure using our telescopes. So there are three different approaches by which we can actually observe this signal. First thing is global 21 centimeter signal. Second is statistical detection, that is through power spectrum, bispectrum, and all other statistics of the signal. And then direct image, like you have ionized regions, you image them. Like when you observe a galaxy, you see a very clear image. So you can do similar imaging, but that is the most difficult among these three because you need enormous amount of sensitivity because your signal is very weak. Okay, so now with this background, I'll now take you to this modeling of this 21 centimeter signal. There is a lot of efforts to actually understand the properties of signal, because since there is no observational constants, we do not know exactly how to exactly model the signal. That's a very difficult task. So how do you model? So this is a schematic diagram that shows you semi-numerical modeling technique, which is very approximate modeling but very fast. And why we need fast simulation, I will discuss. So first, what we do, we simulate dark matter distribution at very large scales, like 1 gigaparsec box we simulate up to redshift 6. Then we identify dark matter halos within these dark matter particles using friends of friends algorithm or spherical averaging method, right? These black circles, sorry, the red circles are locations of dark matter halos. And then what we do that normally the dark matter halos are the hosts of galaxies and stars. So according to their mass, we assign some luminosity. We can also assign some kind of a spectrum to them. So once we have this list of luminous sources in our simulation, we adopt we simulate ionization field in our universe. So this is the ionization field, simulation of ionization regions. The red regions are ionized regions, and blue regions are neutral regions. So this is I think a simulation from the middle stage of reionization. Now the technique that we use, there are several techniques, but the one we use is semi-numerical simulations and 1D radiative transfer technique. I'm not going into the detail, but if you are interested, I can obviously talk about that after this talk. So once we have this field, so this is the field of XH1. I told you, right? XH1. So XH1 is 1 for the blue region, and XH1 is 0 for the red regions. Now, to calculate delta TB, we need to multiply that field with all other quantities. So we do that, and we finally get this simulated 21 centimeter signal, which is delta TB map, right? So this is a very now why can't we do a full radiative transfer hydrodynamical simulation? Because the problem is that you need to simulate gigaparsec box, and on the other hand, you also need sources. You need to resolve those sources, and that is a very difficult task. You need extremely high dynamic range simulation, and this is not possible with the computation resources available. And also writing the code itself is a huge task, right? So, but this kind of simulation we have compared with hydrodynamical simulation, and these give actually fairly very good matching with the actual full simulation. Right. So once you have this simulation, sorry. Right. So as I said that there are three approaches to this problem to understand the epoch of ionization. One is measurement of global signal. So global signal, 21 centimeter signal, essentially is spatial average of delta TB. So we have spatial distribution of delta TB for a particular redshift and for a range of redshift. So we basically take spatial average, and what we get is one number at one redshift, and that is called global 21 centimeter signal. So basically, you can see the plot on the right. It plots temperature as a function of redshift, and you see this dot line is CMB temperature. It falls as 1 plus Z. Then you have this red line, which is the IGM temperature, which falls as 1 plus Z square when there is no heating. But during epoch of reionization, you have this heating due to X-ray sources, so that goes up. And then spin temperature is in between these two. And you see, as I told you, that when spin temperature and CMB temperature they are same, you will have zero signal, right? But you see that spin temperature, this dash line is same very early at redshift beyond 200. So that means you will not have any signal beyond 200. But then because of this collisional coupling, the collision between hydrogen atom and hydrogen electrons, the spin temperature decouples from the CMB temperature. So this you have this window when we can have non-zero signal, and that belongs to dark age. And then again it catches up, the spin temperature catches up the CMB temperature. That means again you will have this zero signal, but then you have this sorry, this should be Lyman alpha coupling. Sorry, this is not collisional coupling, but it is Lyman alpha coupling. So two decoupling method, one is collisional coupling and another is Lyman alpha coupling. So the Lyman alpha coupling actually is very dominant when you have sources just at the beginning of cosmic dawn. So Lyman alpha photons will actually will help the spin temperature to decouple from the CMB temperature. So again, we have this spin temperature which is very far from the CMB temperature. Now we have two windows, one during dark ages and another during cosmic dawn and epoch of reionization, when you have non-zero delta TB, right? So these are the two epochs you can observe using H1 20. Sorry. Here no, the gap is okay. So here you will have no signal. You have zero signal, because your this collisional decoupling becomes ineffective after redshift, I mean at redshift less than 50. So you have zero signal here. Yes. Then again, Lyman alpha source coming from the fast sources, they start decoupling the spin temperature. Then again you will have negative signal, and sometimes positive during the epoch of reionization. Right. Now, okay, so this global signal, there are various global signal experiments, many global signal experiments that actually trying to measure this kind of signal, the signal as a function of redshift only. They are not bothered about spatial distribution in the signal, but they want to measure the delta TB as a function of redshift. So first such experiment is named as AGES telescope. It's a very small telescope. It's not like a big telescope that we see today. It is called suitcase telescope. So you can actually pack the whole telescope inside a suitcase and move it around. So it is AGES telescope, and they first reported in 2020. They reported that they have detected the global 21 centimeter signal from redshift, say 11 to around 20, and these dot points are results from the AGES experiment 2020, and it was published in Nature. So that created huge amount of excitements in the community. There are two reasons. For example, one point is that the signal strength at redshift around 17, they measure the of course signal is negative, and they measure the signal to be minus 500 millikelvin. However, this minus 500 millikelvin is not expected from standard calculation. So from a standard calculation, which I showed on the left plot, you see from a standard calculation, you expect from minus 100 to 200, minus 200 millikelvin signal. Okay, but from experiments you get minus 500 Kelvin, and that's a problem. You need either these results are wrong, or if you believe it to be true, then you have to come up with some explanation. So there are two different avenues by which you can explain. One is that you lower your spin temperature. That means you cool your baryons much faster than the standard case. So and then that is called excess cooling. Another line of explanation is you raise the background CMB temperature, and that is the radio excess or radio background. So Devasisda and we myself and Devasisda students actually worked on this problem for some times, and we actually gave some idea like how can we explain this and constant models, right? Okay. Now this around 2022 Saros experiment that is conducted by RRI, people at RRI, India, they have similar experiments called Saros, and they came up with their results, and they actually ruled out existence of such kind of signal. So they said that they could not find such kind of signal in their experiments. So now we do not know who is right, whether AGES is right or Saros is right, or maybe both are wrong. I do not know. But still debates are going on. But the thing is, the important thing is that these results has created lot of excitements in the field. Particularly now you have possibilities to have particle physicists. I mean, they got very interested, because now interaction between dark matter and baryonic matter can create such kind of signal. So there are a lot of models, huge model, large number of models that explain that, and we have also our own models to wrote a paper. Okay, so that was about global signal. Then second part is that fluctuations in the 21 centimeter signal. So now we want to have more information. So this is an image from our simulation. It plots the delta TB, right? And the box is of the of 160 megaparsec, co-moving megaparsec. It's not relatively small box, but we see this these regions are ionized regions, and these are the neutral regions. Now, as I said, these ionized regions will have zero signal, and you have some positive signal outside. So there are fluctuations in the delta TB, and you can, the standard way to quantify the fluctuations is decompose them in Fourier modes, right? So if you decompose these 2D fluctuations in different Fourier modes like this, and you can calculate power spectrum. Yes, if you just calculate delta TB square, and that will give you the power spectrum. So power spectrum is the quantity that quantifies the fluctuations in the 21 centimeter signal. Now, the primary goal of this ongoing telescope and of course the upcoming telescopes is to actually, this is the first their target to measure the power spectrum of H1 21 centimeter signal. Now here I show a plot which from our simulation that calculates power spectrum as a function of k, that is a Fourier mode, and y-axis is the power spectrum, and you can see there are different lines, and that corresponds to different stages of reionization. For example, when you start the reionization, your power spectrum is almost follows dark matter power spectrum because there is no ionized regions. But later you have these ionized regions growing, and that will boost the power spectrum at large scale. So you increase the power at large scale slowly, and then when you have everything ionized, your power spectrum will just be zero because you have no signal. These are different ionization fraction, average neutral ionization fraction. Right now, so what this plot tells you that if you can measure the power spectrum as a function of k, then that will probably give you an idea about the size of the neutral regions, overall size of the neutral regions, and also about the neutral fraction, right? If you plot the power spectrum as a function of redshift, see if you fix the k to at point 0.1, for example, and if you plot the power spectrum as a function of redshift, you see you have three peak natures. You have this one peak here, one peak here, and one peak here, and that carries an very useful information. For example, as I said that there are two mechanisms, Lyman alpha coupling that decouples the spin temperature, but Lyman alpha coupling is also fluctuating, and that creates a peak at a particular stage. Then you have X-ray heating. So X-ray sources will heat up the intergalactic medium, and fluctuations in X-ray heating will again boost up your power spectrum at some stage, and this corresponds to the fluctuations in the ionization field. So these three peak nature will tell you when Lyman alpha coupling became dominant, or when ionization fluctuations became dominant. So you will get enormous amount of information. And right. So this is about modeling. What is our current status with respect to the measurement? Now again, as I showed, this is the redshift axis, y-axis is the power spectrum, and these are the you see different lines. These are the power spectrum from different models. And these points are upper limits on the power spectrum. So there are experiments like LOFAR, low frequency array at Netherlands, MWA at Australia, and HERA at US. So they actually have taken a lot of data and analyzed it, and they have come up with upper limits on the power spectrum. They could not still detect it, although they have collected large amount of data, but still they're struggling they are struggling with various systematics, and they want to understand the actual reason why they could not detect it. But still, you see, these are the strongest upper limit we have now. This red points, and this is from HERA experiments, and they at redshift between 6 to 7. And but so actually GMRT actually has put up the first upper limit in this business, but that is very high, so I did not put it. And that was also by Uli Pen group, but that is very high. Now the upper limits are going down, right? So hopefully, yes.
They didn't try with the upgraded, the UGMRT.
No, I think they didn't. So they.
No, but
So they.
Remember that GMRT was constructed to be a H1 21 centimeter machine. So obviously, initially the sensitivity was not like that, like Uli Pen did. But now the sensitivity is supposedly much better.
So they collected a huge amount of data with using this newly built GMRT software backend. They published some initial results, also came up with the upper limit, but somehow they realized that this 150 megahertz band is extremely corrupted of RFI. So maybe they felt that there is no point of going further with this situation, because the RFI is.
So I guess, yeah, that's what I heard, that they were trying to do something on this power spectrum from the discussion or something previously, but maybe they didn't.
No, so they didn't pursue it, but now our own Indian group is pursuing with GMRT. I will show you some results from that.
This is power spectrum with a range of K. So what do you mean by that?
No, so I think what they mean that different lines are for different K.
Plotted as wires. So it's not power spectrum at a particular K, correct?
So you mean so these points may not be exactly at 1K, but maybe in this range.
And is a one order of magnitude.
Yes, but your power spectrum, the theoretical power spectrum, is also shown for this range.
I understand.
Yes.
What do you mean by that? Which K? Because different K will have different value of
Yes,
the power
of course.
So is it a kind of average over those K?
No, not like that. For example, let's say this red points. So they have measured it at 1K. But for, let's say, loafer, they have measured it at different K. Yeah.
I think different instruments based on the situation measure at different K.
Yes.
But they are just listing all of them
They are listing
together because in the real power spectrum, in that kind of small range, you don't really expect
one order of magnitude.
Yeah, that's right. But I think this is a function of redshift.
No,
right?
it's not that.
No, I'm saying this is a function of redshift.
What is the function of redshift?
Yes. So then one can calculate that there will not be huge difference in power between 0.03 and 0.4 megaparsec inverse in this.
You see that parallel plot that he showed.
That is one. That is one.
It's very flat.
No, that is one.
At one at redshift of one.
No, that is for K equals to some particular K.
I think we should not read much from this plot. I think they have just summarized the current. Yeah, at least 2 orders of magnitude above the any. No, so meerkat is basically their frequency is much lower, so they can measure at post reionization, for example. They don't have UR band. Right. Okay, so I talked about power spectrum, but power spectrum, if you, as you know, that it captures the Gaussian part in the signal. So it cannot capture the non-Gaussianity in the signal. So if you want to, now your signal is highly non-Gaussian, and that you can see from this plot. So here what we have done, we have plotted probability distribution function of simulated delta TV, and so you see this distribution is highly non-Gaussian. You have long negative tail, and also this has two peaks, so it is far from Gaussianity, but power spectrum cannot capture it. In order to capture the non-Gaussianity in the signal, you have to actually you have to go to the higher order statistics like bispectrum or trispectrum. So we have and one point non-Gaussian statistics is skewness. So we have calculated the skewness as a function of redshift using our simulation, and the signal is negatively skewed at very high redshift, then it slowly goes towards the positive, and it becomes positive at some point, right? So it is but the more optimal way to quantify non-Gaussianity is
Yes.
yes.
Yes. Colors are what?
No, so I'm not going into detail, but since you have asked me, so this your blue line and you have this yellow line. So this blue line is using delta TP, where we have assumed tau, the H1 optical depth, to be very, very small, so that we can approximate e to the power minus tau as 1 minus tau. However, we have first time noticed, yes, but first time in this, so we have worked on this with my students. So first time we noticed that this tau may not be very small. Yeah, it can be substantially large, and so if you have to model the delta TV more accurately, and if we do that, your signal non-Gaussianity actually drops a lot. So we have a full paper in MNRS published recently, where we have discussed all these things in detail.
This is changing when your signal is going from absorption to emission.
Sorry, repeat it.
Your skewness is
Yes,
changing
yes.
when it is going from absorption to emission.
Yes.
That point it is changing.
Not only that, but you have these three different regimes. You have a Lyman alpha dominated regime, you have X-ray dominated regime, and then you have ionization dominated regime. And your skewness is very, very different in these approaches, in the three different epochs. And one can actually, so now I'll come to this, and then you will understand why it is so different. So what we do, that we calculate bispectrum, because that is the optimal way to quantify non-Gaussianity. So bispectrum is basically the Fourier transform of 3-point correlation function, but you can also calculate using this equation. So we plot the bispectrum as a function of redshift. Just focus on one line, that is red line. I mean, these are for different models, but you see at redshift, high redshift, it is negative, but then it remains negative for a long time, and suddenly it becomes positive, and that's because at this point of time, your universe was transformed from being X-ray dominated to sorry, not that. So your universe is transformed from being Lyman alpha dominated to X-ray dominated. So when you have Lyman alpha coupling strong, your signal is negative. So that's why you have this negatively skewed signal. But once you have heating sources, you suddenly heat up your intergalactic medium, and then your signal becomes positive. So your signal actually becomes highly positive. So there's a clear signature of this transition, and you don't see in power spectrum, because power spectrum by construction is positive. So this is a better way to understand the different phases of cosmic dawn and epoch of ionization. Now this is very favorite work of mine, and I have been working on this for a long time. So this is basically we have applied a mass filter technique. So why mass filtering technique? So so what we do here, that we know there are many bright sources from JWST, from HST. There are quasars, there are galaxies, and we expect that there will be big ionized regions around it like this. So we simulate that. So let's say we have very bright quasars, extremely bright quasar. So we have this ionized, big ionized regions around it. And then this kind of signal is actually, we can calculate the form of this signal very precisely. So the form of the signal is known, and we use that as our filter, right? I mean, of course, the radius is not known, ionization fraction is not known, but we can keep those things as a parameter, free parameter. So zero, zero, zero. But when you observe, so this is image, but when you measure it in visibility, you will have this Fourier transform of this will give you non-zero, right? So you have this Fourier Bessel function. So now we know the form of the signal. So sorry.
That left side image. So is it the zero-based image or
No. This is simulated image. This is simulated image. So we have assumed the source properties from there is a very strong quasar at 7.1. So we have assumed the properties of that sources, and we put in our simulation, and we simulated this, right? So now we have this, we know the kind of signal we expect, and then we multiply. So we have used the match filter because system noise is extremely high here. So we use match filter to actually optimally combine the signal and enhance the signal to noise ratio. And in this signal, so this is H1 signal, but you also have these foreground sources, point sources. We add up everything together, system noise, and then we applied our match filtering thing, and then we have studied whether SKA like telescope can detect such ionized bubbles, individual ionized bubbles. We are not talking about statistical detection, or we are not talking about global signal detection, right? So, and we could show that SKA can detect with 100 hours of observations, SKA can detect this kind of ionized bubbles. So this is a work which was published in 2014, and my student Arnav actually, so who actually joined here as a PhD, but then he moved to Jadavpur with me. And so we submitted this abstract to the recently SKA meeting, and that abstract was selected for plenary talk. So this is we are very happy about that. So people are yes, so Chandrasekhar actually did this simulation. Yeah, so Chandrasekhar recently finished his PhD, and he moved to Israel. Yeah, at Israel Open University. Yeah. So he got one prize postdoc fellowship there. Yes. So Chandrasekhar, I was his co-supervisor during his PhD. So yeah, so we are now very happy. So we are pursuing that. So we went on and observed that with GMRT to study the prospect of detecting that kind of sources. The last part of, so how much time we have?
It's 5 minutes.
Okay. Okay, so I'll finish that by the last part that of the talk that is on square kilometer array, and I have been so I have been involved with this almost 10 years. So square kilometer array is basically it is upcoming telescope and the most sensitive radio telescope, and it has two different components. One is called SKA low, that will be built, I mean, that is being built in Australia, and SKA mid that is being built in South Africa, and SKA low actually, which is relevant for this EOR study. And so you can see this is one station. So it's not like this kind of antenna that we are familiar with. This is like one antenna, but this is on the ground, and it will be electronically rotated. And you can see these dipoles from here. And there are already, several stations already built, and you can see the full scale layout. So one station diameter is only 35 meter. And okay, so there will be 307 such stations for A star. It is not full SKA because the funding available based on that, they have decided to have these 307 stations. And then it is 5 to 10 times more sensitive than existing most sensitive telescope like LOFAR or GMRT at this band. And then it will operate this 50 to 350 megahertz, which will cover the entire cosmic dawn and epoch of radiation. So the corresponding redshift is 3 to 27. And yeah, it will have this arc second like resolution. There are several science goals for SKA, and the one we are interested in is cosmic dawn and epoch of radiation, and also cosmology. So we can also study cosmology using SKA. Like you can measure omega matter, omega lambda, H naught, all these things you can do. And these are the other science working major science cases, because this is a multi-purpose instrument. And there are currently 12 members, and you can see India is one of the full members at this moment. And yeah, so the construction timeline. So you have this. Currently, we are we are supposed to be. Currently, what I've heard that they have completed constructing 4 dishes. They have connected all the fiber optics cables and verified it. So we are moving on time, and then so since we have this SK, India is a full member. So in India we have SKIC, so S square kilometer array Indian consortium, and Presidency University is one of the member institution. And Somudip, I think he's representing in the SK board. Right. So there are 8 science working groups formed under the SKIC consortium, and one of the science working group is epoch of radiation and cosmology. And currently we have this 150 members. All of them not are from Naroda students, but many of them. Sorry, my.
Well, some are students.
Correct. That's
Yeah, but in a sense you are right that I mean.
I mean, there are some of
Yes.
like
Yeah, it was just at some point worked on this, and Sid Sethi from RRI. RRI group have this global signal measurement group, right? So he has now retired from RRI, but he of course is part of this collaboration. Right now, these are the some of the numbers, and you can see gender ratio, not that encouraging, but not that bad. Okay, and this is how we are distributed in India. So observation also, we started our, so currently this group is actually, I have been asked to serve as a chair of that group. So we have initiated a range of activities as a part of SK India UR group. And one of the major activities that we started our observational program with GMRT at band 3 and band 2, because band 3 also we can do cosmology. So I'm not going into the details, but there are some results. For example, in this work, our group members have measured the synchrotron power spectrum, galactic synchrotron power spectrum, which is one of the major culprits that we need to get rid of. I mean, for continuum people, this is the signal, but for us it is very bad. So this is the first, this is the power spectrum. And also, if we remove the radio point sources, we can go down 2 orders of magnitude in the power spectrum. So this is the power spectrum of the full signal. But if you remove the point sources, the signal goes down by order of magnitude, 2 orders of magnitude. So we are heading towards the right direction, and we have learned many lessons while analyzing this data. We have identified many systematics and the real problem. So we are learning. So, and these will be these are very useful for actual data from the SK. So GMRT, in a way, it actually helps us to learn various things because it is extremely complicated things. Reducing, analyzing radio data is extremely complicated. So now we have come up with our own upper limit on the power spectrum. Of course, this is in post-reionization. And that power spectrum actually is very competitive with the other groups. And this is from very recent results. And so this Ilahi et al., who is now currently postdoc at IIT Chennai, he is doing a lot of work. So I'm showing the upper limit power spectrum. And this is again our power spectrum measurement from UR frequency. Srijita Pal, so she has actually worked on that, and this is the power spectrum from GMRT using 150 megahertz band. And people are actually continuing this study, right? So we have been we've been actually working on various fronts, and then so major part, of course, is actually understand the data, and of course, once we have data, we need to interpret that. And for interpretation, actually, we need simulation tools. So our group members actually developed various simulation tools that will allow you to simulate 21 centimeter signal. And these are the simulations that developed by our group members. Riayan Yuga, developed by Rajesh, who is now at faculty at NIT Tirupati. No, I mean, Warangal na. I will na. But he has, yeah. And script developed by Tirthoda and Grizzly. This is one of the courses that I was involved in when I was at NCRA. And Raghunath now, he is a Ramanujan fellow at ISAR, Kolkata, recently joined. So he is doing a lot of work that. Then there are tools. I'm showing these tools because these are publicly available. We made these publicly available because we are working as a group, and anyone can actually go and actually install and actually do some kind of projects. Calicut, yes, yeah. And so if you are interested to learn about this 21 centimeter cosmology, there are two lecture series, one by, of course, Somnath Bharadwaj, and another is set of lectures by Tirthankar Rai Chaudhary. And these are very beautiful lectures. So it starts from really starts from the basics. So anyone can actually follow that lecture. So if you want to get into this field, these are the good lectures to start with. And then we have bi-weekly discussions. So every alternative weeks we have meetings, and anyone can join. And so far we have around 190 discussion sessions, and it has been running over last 10 years. So that is like a presidency colloquium. These are very helpful to keep us. We can update ourselves, right? And then we also participated in the SKA data challenge. So SKA sometimes gives you some data, and they ask you to calculate something, and so they have some marking criteria, and based on that, they come up with ranks. So last time our group came second. This one group, Akash Ganga, came second in the UR inference data challenge, right? So if you want to be member, SKA India Science Working Group member, just fill out this form. And if you want to be international member, then you can also fill out this form. We have one YouTube channel where we have all these lectures recorded. And the one important point that, so this is again the project report that we submitted to the NCRA. And this is, so this summarizes all the science details in the, right? And one of the, another thing that we do on regular basis is we organize workshop on every year, and school every alternative year. So for example, the next workshop and school will be at TIFR, organized by Girish. So these are some of the pictures, and you can see this picture. This is the one that we have organized at Presidency 2017. And I mean, these are the other, during COVID time also we organized online. And you can see your teachers, maybe Suchetana, yeah, and me, and Ritavan maybe somewhere, I don't know. Yeah, the quality is not that great. So yeah, we can see RI director who attended that conference, all the lectures. Right. So at the end, says so you can read through it, but the one important thing that this is a field which is very exciting, and this is also the last frontier of. I mean, people say that this is the last frontier of cosmology. So, and it's very difficult. The main task at this moment is to understand the data. I mean, there are so many systematics. You have foreground sources which is 1,000 times, 10,000 times stronger than the signal. So you need to understand each and every detail precisely. So these ongoing telescopes are actually helping us to understand. But I think SKA will be the ultimate telescope, and we hope to get some important results from SKA. And our groups, science working groups, working really hard to contribute to this field. Okay, so thank you.
Even the SKA India logo was.
Yes, yeah. So yeah, so that I wanted to actually share with you. Yeah, first slide.
No, but even India was. Yeah, this one, right?
Yes, that one.
Yeah, we can show you at the front. Yeah, so this is the logo actually designed here at Presidency at this building.
By an undergraduate.
Yeah, by Konoya Malakar. She was master students at the time. Yeah, so there was a national I mean, NCRA announced a national competition for logo design for the SK. And so Konoya, I knew she is very smart in Python programming. So I told her that we can also do that. So we discussed that, and we submitted two designs, and this was selected for the SK official SK India logo. So yeah, we're very happy about that.
That actually talks about these are the radio, like the
Yes.
antennas, and
Yes.
the color is like India's flag and all that.
Yeah, and then we have three things because we want to also share the message that we need to join hands. This is not for one person to do that, but we really need to collaborate. We need to form groups because this is something which we are lacking. So
Sharing.
yes, yeah.
This is like, this says, if you need people, we can supply people.
And
Okay.
this is actually done using a Python code. It's not hand drawn.
Yeah.
It's a Python code that
So
has.
Gona did everything with Python.
Yeah.
So she made the Durga sort of face with Python. She made some other like cartoon things. With
Yeah, and
Python.
then she actually simulated thunderstorm with Python by solving the.
Yeah, but that is a physics problem. I'm saying that even artistic things.
Yeah, and she
she
was
will do
teaching
it.
course like that, right? That
Yeah, she
art
did. She
and-
did at Brandeis. She taught a course on arts, artistic applications of programming.
Programming or something.
Okay, questions? There were quite a few questions in between, but okay. Go ahead.
Can you elaborate on a little bit on the numerical simulations while in the 21 centimeter simulations that you showed for that?
Yeah, so I have quickly gone through it.
There is a slide which
Yeah,
is pretty elaborate.